So this is Math466, if memory serves. Yes? Advanced Applied Analysis, Lecture 16. So what we're going to do today is we're going to finish off all of the stuff on recurrence relations, and then we're going to move to talking about spacings between events. And so the idea is, how do you attack a whole slew of questions like this? I'm not going to prove the most general results, but I know a lot of you are going into situations where you're going to have to try to model and predict how things are going to behave. One of the biggest questions you have is, how long do you have to wait before the next event? Does anybody know what company is really good at predicting wait times? What company, what kind of service industries do you think have to be really good? If you say the airlines, you will fail this class.
Well, I was thinking jokingly saying the DMV, but
I'm just thinking of Patty and Selma. No, Patty and Thelma, is it? From The Simpsons? No, it is not the DMV. What company do you think has to do a really good job of predicting weights? Restaurants should hopefully do a good job predicting weights. Do you think they do a good job? Amazon. UPS in terms of how long it will take for the package. For restaurants, is it better to overestimate or underestimate?
That's a really good question, actually.
So if you tell somebody it's going to be a 50-minute wait and it only takes 20 minutes, are they happy or upset? Happy. If you say it's going to take 10 minutes and it takes 20 minutes, are they happy or upset? Upset. So a lot of it is managing people's expectations. It's much better to tell people that you're taking them earlier than expected than to tell them you're taking them later than expected. What's the danger of telling somebody 50 minutes when it only takes 20? They might leave. And in fact, they will frequently leave. Oh, it's not worth waiting 50 minutes. So you want to have a really good understanding of wait times. Disney is really good at wait times for rides. Yeah, I'm talking about this in operations research, where every now and then they give red cards to people in line so that they can actually make sure that the line wait really is what they expect. It's a really simple way to keep updating. So how do you determine what the wait time is between various events? So what are the events we could care about? They could be zeros of the Riemann zeta function. They could be fractional parts of n alpha mod 1. They could be energy levels of heavy nuclei. They could be eigenvalues of matrices. So we're going to build up a framework to talk about something like this. Some of the results are absolutely surprising. And so I will give them as suggested exercises for you to do. If you want me to make them more formal, happy to do so. So let's finish up recurrences. So I'm going to sketch the proof. I'm not going to go through all the details, but I'm going to do enough to give you a sense. Let's say we have a Binet formula, and let's say we know, an is c1 lambda 1 to the n plus c2 lambda 2 to the n plus dot 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 plus ck lambda k to the n. And let's assume that there's a unique eigenvalue that's largest, and it's greater than lambda 2, which is greater than or equal to lambda 3. So in this case, this term dominates. And what you can essentially do is you can write it as c1 lambda 1 to the n, 1 plus some error term. And how large is the error term? Well, I'm going to have at most k minus 1 pieces. I'll have the maximum of the CKs. Technically, I shouldn't, of the CLs. Technically, I shouldn't include C1, but it doesn't matter. I'll then have all of these are at most lambda 2 to the n. And then I'm dividing by lambda 1 to the n. And now what you notice is this over here, lambda 2 over lambda 1 to the n, lambda 2 over lambda 1 is less than 1 in absolute value. So this is basically, c1 lambda 1 to the n, 1 plus, we'll call it some delta, I guess, big O of some constant times delta to the n, where the absolute value of delta is less than 1. And then we can argue exactly as we did for the Fibonacci's, that this is going to become exponentially small. So if you choose any small epsilon window, eventually this is going to be just at a very sliver of that window, and it can't really change things that much. So as long as we're in a case like this where we have one eigenvalue that's largest, we will have benefit unless a terrible thing happens about this eigenvalue. What's the terrible thing that could happen about this eigenvalue? There's only one way we wouldn't have benefit. So when we're looking at benefit, we want to look at like the log base 10 of an. So that would then be the log base 10 of c1 plus n log base 10 of lambda 1 plus the log base 10 of something like 1 plus big O of c delta to the n. We know this piece doesn't matter. We know this piece is just a shift. So when would we have benefit?
That's rational.
If that's
Rational.
if it's rational?
Irrational.
Irrational. Right. So if the log base 10 of lambda 1 is irrational, it's benefit. If it's rational, not benefit. So think of it, imagine lambda 1 is 10. Then what this is saying is eventually your sequence looks like some constant c1 times 10 to the n. So maybe it's 2 times 10 to the n, 2, so it's maybe 2, 20, 200, 2,000, 20,000. How much do I have to lecture for today? Something like that. And then the other stuff can't really change the first digit that much. Now, interestingly here, that small change will be enough to change the first digit always. It will still be non-benefit. But now, if it's positive, it will not change the first digit. And if it's negative, it will change the first digit down. So in terms of what the distribution is, if this is rational, I don't know. But as long as it's irrational, we're fine. OK. So the argument is fortunately the same as what we did before, so we don't really have to do anything. The only difficulty is if we don't have a formula like this. So the problem is, what if there's an eigenvalue with multiplicity? What happens in that case? Or, not eigenvalue, root of the characteristic polynomial. So how many of you have done the analysis of characteristic polynomials and handling multiple roots? OK. Have you seen the proof of why the formula is now a polynomial in n? Or were you just told that that's what it is?
No, I think we talked about this in my class.
OK. OK.
Just like using characteristic polynomials to solve.
Right. So the difficulty is, if the characteristic polynomial has, degree k and k distinct roots, then we can write down a generalized Binet formula. But the problem is, what if there's a repeated root? So we have So it's just good to know how to handle this last remaining case. So we have, an plus 1 is, c1 an plus c2 an minus 1 plus ck an plus 1 minus k. So we have some kind of recurrence like this. So we guess an is r to the n. It gives us the polynomial r to the n plus 1 minus c1 r to the n minus c2 r to the n minus 1 minus ck r to the n plus 1 minus k equals 0. We then pull out an r to the n plus 1 minus k, and we get r to the k minus c1 r to the k minus 1 minus c2 r to the k minus 2 minus ck equals 0. And then we get roots R1, R2, Rk. And the issue is if there's multiplicity. How do we find the remaining solutions? So if we have k distinct solutions here, then we can take a general polynomial, and the general solution, if distinct, is going to be, say, alpha 1 R1 to the n plus alpha k Rk to the n. And then you just choose alpha 1 through alpha k to match the initial conditions. Okay. So what I want to do is I want to just sketch what you would do if you have repeated roots. I'll state the result, and then rather than prove the result, I will try to explain to you both why it's reasonable and how you might have discovered that. So again, most of you, this is the advantage of having a small class. I know what most of you are either going to do or planning on doing, for the next couple of years of your lives. And as of now, no one is, I think, planning on going into a situation where you will be solving generalizations of recurrence relations like this. Yeah, I see a lot of heads going, nope, I'm done with this. So what I want to do instead is I want to concentrate on the thought process as to how would you get to that solution. Because it's the thought process that you can generalize and use beyond Williams. The actual math you're not going to use, but how you attack it. So if root of multiplicity m, what you do is you have alpha 1 r to the m, r to the n, plus alpha 2 n r to the n, plus dot dot dot, plus alpha m n to the m minus 1 r to the n. So basically, instead of having m distinct roots, if we have a root with multiplicity m, we first have the root to the nth, then we have n times the root to the n, then n squared times the root to the n, all the way up to n to the m minus 1. So we have the right number of solutions, and all that really changes is a polynomial. So one way you could see this is you could factor the characteristic polynomial. You would know that you would have to have a multiplicity, go through and see what would happen. So proof algebra. Okay? I leave it as an exercise for the interested reader, if one exists, to go through and do the algebra. I don't think such a reader exists or listener exists in this class, so instead I want to motivate how you would come up with this. So let's think, we're going to tweak our system. And this is a really nice math concept, that a lot of times you have a singularity where things blow up. So what you do is you push yourself just a little bit past the singularity where things are nice. Solve the problem, and then take a limit as you converge back to the singularity and hope that you can somehow extract something meaningful. So it's a really nice idea. So what we want to do is we want to tweak the original problem so that we have distinct roots. Do you think we could adjust the coefficients just a little bit so that the roots become distinct? I mean, we've got the characteristic polynomial. So tweak the polynomial. Let's say right now we have, r minus r1, r minus r1, r minus r1. Let's say we have it m times. We could do r minus r1 minus epsilon 1, r minus r1 plus epsilon 1 maybe, r minus r1 plus epsilon 2, dot, 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 dot. We could just tweak the roots by very small amounts and make them all distinct. And then we could get a new recurrence relation. Yields new recurrence similar to old. So do you agree that if we make all the epsilons really small, the new recurrence relation will have almost the same coefficients? Choose epsilon if you want as like 1 over 10 to the googolplex. And if we do small little tweaks like that, we'll make the roots distinct. And we'll have a new recurrence relation that will have distinct roots. So I'm going to just concentrate on the case of a multiplicity 2 root. Okay? if we can do what's going on with two roots that are the same, we can do what's going on in general. So assume for your an plus 1 equals c1 an plus c2 an minus 1, have r1 equal r2 equals some value r. So we can tweak the roots a little bit. And so we tweak. And now we'll have, an plus 1 is c1 maybe of epsilon an plus c2 of epsilon an minus 1. And we have roots r1 of epsilon and r2 of epsilon. So here, if you want, the simplest thing I can do is add epsilon to one root and subtract epsilon from the other root. Very simple thing. If I had more roots, I'd have to do something a little bit more involved. Not a big deal. I could add 5 epsilon to the first, 4 epsilon to the second, 3 epsilon, 2 epsilon, nothing, negative epsilon. So it's not too bad. So we know the solution is alpha 1 r1 of epsilon to the n plus alpha 2 r2 of epsilon to the n. Right? So several of you should know me now. What is the only thing I will say New York does better than Boston? The streets. The grid pattern of Manhattan is a much better coordinate system than Boston, especially near Beacon Hill and Comm Ave. There's a lot of parts of Boston that are just interesting to get around. The whole point of linear algebra is choosing a good basis for your problem. This is supposed to be a capstone class. I'm supposed to be tying together things you've seen. Right? One of the big ideas of linear algebra is choose a good coordinate system. If you're lucky, you can construct the universe in such a way as they did in Manhattan to have a good grid. But in general, you're going to have a complicated problem. What coordinate systems do you want? I know in previous years we've talked about if you have an ellipse like this, you choose your coordinate axes like this. You write down your ellipse in this system, and then you convert by rotation to the system you want. So I'm going to look at, instead of this combination of roots, I'm going to look at my solutions as r1 epsilon to the n plus r2 epsilon to the n, and r1 epsilon to the n minus r2 epsilon to the n. I guess I'm putting the n on the other side. So instead of using r1 and r2 to the n as my fundamental solutions, I'm using these as my fundamental solutions. Can I go from these to these? Yes, in fact, it's very clear. These are written as, add these two, subtract these two. So clearly, I can represent these, anything that I can get with a linear combination of these, I can get with a linear combination of r1 to the n and r2 to the n. What about the other way around? Can I get any linear combination of these two and get me anything over here? Well, if I add these two, I just get twice r1 to the n. If I subtract, I get twice r2 to the n. So I can actually get twice r1 to the n and twice r2 to the n. Okay, if I can get twice, I can get half of that. So there's no difference between the space of solutions here, I'm going to call this beta 1, beta 2. And there's no difference there. So do you agree that these are the same solutions? I'm going to divide this by r1 to the epsilon plus r2 to the epsilon. Am I allowed to do that? At this point, I'll probably assume that r1 is not equal to 0. Although since these are now made to be distinct, I don't know. Is this going to change the set of solutions? So am I allowed to just divide by this? Does it change the set of things I can get? What can I do to beta to adjust for this?
Yeah, we multiply beta by that.
Yeah, so this is a new beta. So I'll call it beta tilde. It's just some fixed number down below. So if I looked at this as my fundamental solution, there's really no difference because I'm just dividing it by a constant. I can adjust beta star by that constant. All right? Let me divide this by a constant. R1 epsilon minus R2 epsilon. And I'll adjust beta by a constant. So do we agree that these have the same set of solutions as that? Now what should we do? So what should I do now? What problem am I trying to solve? I'm trying to solve the original recurrence. This is a tweaked recurrence. What should I do now? Take the limit as epsilon goes to 0. If I take the limit as epsilon goes to 0, this denominator just goes to twice r. And this goes to r to the n plus r to the n. Okay, so the 2's cancel. So if we take epsilon going to 0, we were going to get beta 1 tilde over r times r to the n. Right? You could write this as r to the n minus 1, but I like to write my solutions as r to the n. So I'll just incorporate that r over here. So I'm assuming the root is not 0. If the root is 0, then the recurrence relation is quite boring. You just keep getting 0, 0, 0, 0, 0. So do we all agree that this first term is going to converge to r to the n? Did you do this in Budapest?
I don't think we proved.
Okay, so it was just stated. It was just stated, right. It's a nice proof. I saw this, I think, when I was taking differential equations. I remember my professor motivated this. Let's look at this limit as epsilon goes to 0. Which would this go to? I'm sorry? Well, this is the more interesting limit. The numerator goes to 0, right? What does the denominator go to? 0. So we have 0 over 0. So there's lots of ways we could do this. So we need to understand the limit as epsilon goes to 0 of r1 epsilon to the n minus r2 epsilon to the n over r1 epsilon minus r2 epsilon. What does this look like? Yeah?
Why is it? I don't see why the first term isn't multiplying to 0.
Well, because r1 epsilon goes to r. The two roots are converging to r. Yeah, I mean, I'm tweaking the roots. So if you want, let's be explicit. Let's make r1 of epsilon equal r plus epsilon, and let's make r2 of epsilon just r. We don't actually have to disturb both roots. If we just disturb the first root, that's enough. And so we'll have two distinct roots, and now as epsilon goes to 0, they both converge to r. And so in that case, we'll get r to the n plus r to the n over r plus r. So we get 2r to the n over 2r. 2's cancel, and I'll keep one of the r's outside. I could have had the other one be r minus epsilon if I want. It's not going to change things in the end. It would then just change the denominator. Now would be 2r plus epsilon versus 2r plus 2 epsilon. For the next step, it's actually a little bit more convenient to do r plus epsilon and r. Because now if I plug that in here, what do I have? I will have this equals the limit as epsilon goes to 0 of r plus epsilon to the n minus r to the n over r plus epsilon minus r. And again, I could have done r plus epsilon to the n minus r minus epsilon to the n. What does this look like?
The limit n times r plus epsilon to the n minus 1. You just take
Okay, so we could take L'Hopital, and then we take L'Hopital by taking the derivative with respect to epsilon. So we could definitely L'Hopital it, but I think if you step back to an earlier class, which you may not have taken at Williams, you might recognize this limit. You can definitely use L'Hopital, but L'Hopital is overkill.
It's the differentiation of r to the n.
Yeah, it's the derivative of r to the n, right? If I want to take the derivative of r to the n, it's r plus epsilon to the n minus r to the n over epsilon. So by definition, this is just n r to the n minus 1. So if you want, this piece over here converges to beta 2 tilde, and I'll put one of the r's over here, n r to the n. So this is a proof when you have one repeated root that it generates r to the n and n r to the n. The rest is just doing some bookkeeping in terms of how you want to write the constants in front. You look like you want to say something.
How did the n minus 1 become n?
Because I put an extra r down below.
All right, sorry.
And so I'm just trying to write it as n r to the n because that's how we want to write things in Binet's formula. So this constant over here I'm going to give an r to. I think it's much better to do that than to have things of different degrees. I want to have all my terms to be degree n. If you think from a computational perspective, then you could calculate r to the n for both of those. So what I like about this is it suggests where the n r to the n comes from. It comes from looking at a different basis for your solution space. And there's a lot of ways you could tweak. You should check and see that if I used r minus epsilon, I would still get the same limit at the end of the day. Or if I don't get the same limit, it would differ by a constant. If it differs by a constant, that just changes what's over here. All I really care about is that it looks like n r to the n. I don't care if it's 2nr to the n, 3nr to the n. All of those will have the same solution space. Because what we're looking for is we want to write everything as a linear combination of these. If you had 3 solutions, you would have to play these games again and again. And it starts to become a little bit more involved. So if you want, it's a nice exercise. If there were exams in this class, that'd probably be a really good exam question. Consider the case of 3 roots. Can you prove that it would be r to the n, nr to the n, and n squared r to the n? Okay. So is this enough detail for this problem? Okay. So recurrence relations are discrete versions of differential equations. If another math professor were here, he would probably talk about how these equations rule the world or govern the world, maybe emphatically. Difference equations are just discrete analogs. Given how many things can be described by difference or differential equations, it's worth understanding them. It's worth understanding their solutions. In general, it's very hard to solve difference equations or differential equations. We can solve certain types of equations. If it's constant coefficients, we can solve. So constant coefficient fixed depth. And this is what we needed for the Indian 15-game winning streak. If we make the unreasonable assumption that they have the same chance of winning every game, we got a recurrence relation of depth 15 with constant coefficients. Okay. So now it's time to shift to studying spacings. And so this is the next major unit. So consider alpha irrational. Let's study xn equals n alpha mod 1. So what do we already know about this sequence?
Like we're
It's equidistributed. So we know it is equidistributed in 0, 1. Now, if we look at it in 0, 1, the points are going to fall in some order. Maybe x1 is here, maybe x2 is here, maybe x3 is here, x4, x5, dot, 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 dot. So what we can do is we can relabel. So 0 less than equal to y1, less than or equal to y2, less than equal to, less than equal to yn. So let's take the first n values and label them in increasing order. Is it possible that two of them could be the same? Okay, so why can't two of them be the same? It wouldn't violate density, because if only two of them are the same once, although if you think about it, you can get a density violation from this. Imagine x4 equals x9. Would you then have infinitely many things going? Would it become periodic? So basically, if two of these are the same, they differ by an integer, and you get that alpha has to be rational. So if you get, n alpha equals m alpha plus some integer, then you get alpha is equal to k over n minus m, which is rational. So we can't have two of them being the same. So I don't actually have to have less than or equal to. I can actually say that strictly. And so in complex analysis today, we had the issue of we knew that there were always two solutions to something. We needed to just show that the solutions were distinct. And it took us a lot of time in complex analysis to show that the solutions were distinct. Fortunately here, we have this immediately. We can't have repeats. So we have a sequence. And we can talk about the spacings between them. Now, in some sense, the spacings have to be somewhat regular, right? Why do they have to be somewhat regular? It's equidistributed. Imagine one of the spacings was huge, was like a half. Well, then you would have this huge gap where you have nothing. So the spacings have to be somewhat regular. So what I like about this problem is the first question is, what is the right scale to study it? So how far apart do you expect the yi's to be from their neighbors?
1 over n.
Yeah. Because they cover an interval of size 1. There's n of them. So how many gaps do we have? Well, the real question is always, do you consider the gap from yn wrapping around to y1? If you do that, then it's complete. One gap as n goes to infinity is not going to really change anything. So a lot of times you talk about the wrapped interval where the number after yn is 1 plus y1. And you just do that so that you can say the sum of the distances adds up to 1. So we'll have n minus 1 gaps, add y1 plus 1 minus yn. Now we have n gaps, cover 1 unit. So average gap is of size 1 over n. Is it possible you could have a gap of size 2 over n or 5 over n? That'd be twice or 5 times the average value. What about 1 over square root of n? Would a gap of 1 over square root of n kill equidistribution? Would you be surprised? Now, a gap of size 1 over square root of n, this is much larger than the average gap. This is square root of n times the average gap. If you think of a Gaussian, being square root of n standard deviations away, this is an improbable event. So over here, it's probably very unlikely that you would have any spacings as large as 1 over square root of n. So what we could do is we could look at the spacings of the orderings of the ordered n alpha mod 1. And instead of n alpha mod 1, you could also look at n squared alpha mod 1, or n cubed alpha mod 1. And there is a huge dividing line. These all behave in one way, and this one behaves differently. For all n, only see 3 gap sizes. This is a really strange result. You can numerically test this. As a really good exercise, write a short computer program. Mathematica is really good for this because it will do things symbolically. And look at maybe 1,000 values of some irrational number, alpha, 2 alpha, 3 alpha, 4 alpha, up to 1,000 alpha mod 1. Order them. Look at the gaps. And you'll only see 3 values here. In all the other ones over here, they will all have the same limiting behavior. But in this one case, you will only see 3 gap values. It's very interesting.
What are they?
It depends on the number alpha. So different alphas will give you different ones. And it might be possible to occasionally have just 2 gaps. I can't remember if once n is at least like 8 or 9, if you always see 3. But I know you never see 4 beyond some point. And you never see 4 at all. So the question is, how would we attack a problem like this? So when we were looking at the equidistribution of n alpha, we used Fayet's theorem. And the reason Fayet's theorem was so useful for us is we had exponential functions, and when we looked at e to the 2 pi I n alpha mod 1, that was the same as e to the 2 pi I n alpha. That's a geometric series. We can understand geometric series. That's how we went about this. So the question is, how will we attack a problem like this? And again, we want to attack more than just the spacings between the fractional parts of n alpha. We want to look at spacings between maybe energy levels of heavy nuclei, or between eigenvalues of matrices. That's, I think, chapter 15. And so we want to build some tools to attack problems like this. So what I want to do is, we've got about 10 minutes left, is I want to start introducing the language to attack these problems. There's no class on Friday. Use that to work on projects. And then on Monday, we will start doing the analysis from chapter 12. And what we'll do is we will show that we will look at not n alpha mod 1, which is hard. We will look instead, what if we choose big N numbers uniformly in the interval 0, 1? What can you say about the spacings there? And for those of you who might be going off into finance, maybe this is actually something that could be applicable. Is you've got a bunch of uniformly distributed quantities. You're looking at what can you say about spacings between events. So some of that could actually be of use. So the idea, if you want to associate a probability density, well, I'll use the word measure. By abuse of notation, we often use density in places where we probably shouldn't. So what we're going to do is we have a sequence of events. So have events x1, x2, ... xn. And we'll form a measure, mu n of x will be 1 over n, the sum, little n goes from 1 to big N, of the delta spike of x minus xn. So what we're basically doing is we're putting a point mass of size 1 over n at each event. and we're building a probability measure out of that. So we've seen the delta spike before when we were doing our Fourier analysis. This was essentially the limit of, say, maybe a Gaussian where the variance is tending to 0, or some kind of rectangular box or triangle. And then the idea is, if I have any nice function, I can understand what's going on by integrating against this. And when you integrate against the delta spike, it just returns your value at xn. So one of the best things to look at is maybe moments. If I look at x to the m mu n of x dx, and I integrate this from, say, minus infinity to infinity, this will be 1 over n, the sum, n goes from 1 to big N, integral minus infinity to infinity, x to the m, delta of x minus xn dx. Why can I interchange the integral and the sum? Why is this legal? Not bounded. Why can I interchange the integral and the sum? It's what's true about the sum? The sum is finite, right? Sometimes we get so worried about justifying things that we're actually in a situation where there's no problem because it's a finite sum. Now, because of the delta function, this is going to just return x to the m. At what point? At the point xn. So this is just 1 over n, the sum, n goes from 1 to n of xn to the m. So this is the mth moment. And the idea or the hope is that by understanding the moments, we can understand the probability distribution. So this is where some complex analysis would be really useful. In probability, we actually saw examples of two densities that have the same integer moments and the same half integer moments, but not the same quarter integer moments or any other moments. And so the question is, what do you need to determine when two functions are the same? So as an easier example of why real analysis is so hard is I have lost track of how many times I have looked at this function with all of you. So does anybody know which bad function from real analysis I want to write? It has a very interesting Taylor series expansion. For those who are fans of the nothingness from Seinfeld, e to the negative 1 over x squared. Right? If this is, and we'll say it's this if x is not 0, it's this if x equals 0. Was this function explicitly assigned earlier this year? I know I do this in almost every class I teach. Using L'Hopital's rule, you can calculate all the derivatives at the origin as 0. Which makes sense. I mean, if you think about this, take x as 1 over billion, then this becomes e to the negative billion squared. It's going to be small. If you plot this function, it's really flat near the origin. So when we look at the Taylor series expansion of this function, its Taylor series expansion is identically 0. So if I give you the function x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, what function has this as its Taylor series? I'm sorry? Sine. No, cosine is 1 minus x squared over 2 factorial. But I could be thinking of the sine of x plus 24601 over 1701 f of x from before. If I calculate the Taylor series expansion of this, will I get that? Yes. This warns us that if I have a function, is its Taylor series unique? Does one function have two Taylor series? No. You can't have multiple Taylor series for a function. But if I give you a Taylor series, could more than one function have that as its Taylor series? Yes. So this is the inverse problem. So frequently the inverse direction is much harder. And so if I know that this is the output, what was my input that got me there? I don't know. There could be several possibilities. And this is where probability gets really hard, is we need to somehow talk about what is the inverse. And we want to say that if I have something like this and it has an additional nice property, then it's got to be this. I want to somehow eliminate this 24601 over 1701 f of x tagging along for the ride. So the idea is we're going to build up these functions, and one way to understand them is to understand their moments, and hope that by knowing the moments, we can understand the underlying function. Okay? But the whole idea is, given some kind of sequence, we need to associate an object to it that we can apply the tools from analysis that we're developing. And so we'll do it to points that are uniformly drawn in 0, 1, and see what the answer is. And then we'll talk a little bit about applications to the n alphas and the n squared alphas, and then we'll move into random matrix theory. All right, so this is a good place to stop.